Well, thank you very much, Michelle, and thanks to Michelle Servasis and Frank for organising a really fantastic set of seminars. So I'm going to talk about, as Michelle said, photothermal microscopy and the what our thoughts are on resolution limits and how that is affected by heat dissipation. As Michelle pointed out, I have a sort of a background in looking at nanoparticles, and so to me, this field is about trying to make images and learn things about nano objects that don't emit, right? If they emit, the easiest way to look at them is to do fluorescence microscopy. However, if they're not emissive, it's a bit more complicated. And so these are some of the techniques that you could use to look at small particles that don't emit light. You can do photothermal imaging, which is what we'll mainly be talking about today. You can also do a technique called spatial modulation spectroscopy, where you move the sample and look at how that changes the transmission of light. Or you can do transient absorption microscopy. And as we just heard, you can do the interference scattering microscopy. And in my lab, we've tried 3 out of these 4, PHI, SMS, and transient absorption microscopy. We haven't done the interferometric scattering microscopy. Honestly, it looks a little bit hard, but it's a really fantastic technique, so maybe we should try and do that as well. So in all of these, you, as was alluded to, you're detecting a field that goes through the sample or is reflected from the sample that has contributions from the incident light and the scattered light. And the way that we try to do things is to modulate the scattered light in photothermal and transient absorption microscopy. You do this by modulating a pump beam. And then you use a lock-in detector so that you only get that interference term between the incident and the scattered light. So the spatial resolution, right, is going to be limited at best by the diffraction limit of your laser beams that you use. If you're interested in doing infrared spectroscopy for example, to look at nano objects, then you're going to be severely limited by the wavelength of light, right? So the diffraction limit is basically the wavelength divided by 2 times the numerical aperture. And so in the IR, you're hit by 2 problems. One is that the numerical aperture of the objectives is not all that great. And the second one is the wavelengths are really big. Okay, so this is an example of trying to directly image polystyrene beads, not really nanometer-sized objects, but micron-sized objects with an infrared laser. So what we did here is we just focused the laser at the sample and scanned the sample through the beam, and you can see the beads with reasonable contrast, right? It's not too bad, but the spatial resolution is pretty lousy in this experiment. The best we could do is about 8 microns, which is much, much larger, of course, than the size of the polystyrene bead. So the approach that we've already heard from a couple of speakers in this webinar that you can use to improve this is to do a photothermal image where the spatial resolution now becomes limited by the probe laser. And so this is the way that myself and at Notre Dame, in collaboration with Ken Kuno, first did these experiments. So we focus a infrared laser at the sample with a reflective objective. And then now the difference between how we do things and what was done by Jixing Cheng in a previous talk is that we focus the probe beam with a regular refractive objective. So we separate the pump and the probe. Now, the advantage of that is that refractive objectives are usually a lot better than reflective objectives, so we get a much better spatial resolution in doing this for the probe beam. The disadvantages are that it's a little bit more complex to set up, and also you obviously need to look at substrates that are pretty transparent in order for this to work, because the probe has got to reach the sample. And that's not as big a problem as you might, it's easy enough to do in the lab. If you're going to make a commercial device, right, this is not the way it's done. The commercial photothermal spectrometers just use a co-propagating beam arrangement. In any event, the way that we did this is we started to look at some just model samples, polystyrene beads. These are some images, about a 0.5 micron size, 500 nanometer beads. You can sort of clearly see better spatial resolution. If we look at a very small polystyrene bead, we can detect it and see it has a point spread function or a spatial resolution of about 0.3 microns, which is about almost 30 times better than what we saw in the previous experiment with just direct infrared imaging. So you can really sharpen up your spatial resolution a lot by using this little trick where you're detecting the heating from the infrared laser in a photothermal measurement. These experiments were all done on dry samples, so they're just beads on a glass surface. These are some spectra and images at different wavelengths. And, if you scan the laser, you just basically record the infrared spectrum, which is very handy. I'll talk a little bit about the contrast mechanism in a second. You can also do these experiments in more continuous samples, and we've seen some really beautiful images of what you can do in cells. So this is just a very trivial continuous sample. It's a patterned polymer film. You can get a signal out of that. And what our thoughts on how the contrast comes about are that when we have a bead on a dry surface, we're looking at the change in the scattering of the bead. Here, we're basically looking at changes in the refractive index of the field, which basically changes a little bit the reflected light. The reflective indexes of the film, which changes the reflected light that's coming back to the detector. Okay, so we worried a little bit about how the signal arises, and to address that, we did some simulations. So these initial simulations were kind of fully coupled. We calculated the absorption of the bead, the heat dissipation of the bead into the environment, and then calculated the change in scattering cross-section for the visible probe laser. And this is sort of what you see. So I'll show 3 little videos. The first one is going to be the temperature changes that happen when you excite the bead with a 10 nanosecond infrared beam. So that's what that looks like. So you can see that you heat the bead, and the glass surface is on the bottom. So there's a big change in the temperature of the bead from the heating, and a big change in the temperature on the air surrounding the bead. And the reason for that is there's heat transfer to both the air and the glass, but air has a very small heat capacity, so there's a large temperature change in the air. So our thoughts were that the signal comes from the change in the scattering cross-section of the sample, and so that has contributions from changes in the refractive index and changes in the size. And maybe that's not the best way to think about that, because basically the refractive index changes because the size changes, so those two things are really kind of combined together. But this is what the change in the refractive index looks like. There's a big change in the refractive index of the bead, but not much in anywhere else in the system, because, well, you saw there's a large temperature change in the air, but air has a very small refractive index change, so you just don't see it. And likewise, we're just looking at the expansion of the bead, and there's a large change in the size of the bead from the heating. Well, not a large change, but there's a change. And in all these simulations, you can kind of see that the changes in refractive index, changes of expansion, changes of temperature are very small at the interface between the bead and the glass, and that's because the glass is the heat sink here, and it's taking the energy away. Okay, so these are our calculations of how the cross-section changes, and so that's our claim as to what's giving the contrast in these experiments, that you have contributions to the change in cross-section from change in refractive index and from expansion. Interestingly, or maybe not too surprisingly, right, those two things go in opposite directions. So if the bead expands, the cross-section goes up. If the refractive index changes, when you heat a material, the refractive index goes down, so the cross-section goes down. So those two effects kind of cancel each other. So sometimes you'd expect to see an overall increase in the cross-section. Sometimes you get an overall decrease in the cross-section, and it depends a little bit on the size of the bead, right? Or it depends on the size of the bead. And so that's basically what we're monitoring, the photothermal measurements. We change the cross-section and the probe laser picks that up. And I should say, after the very nice couple of talks today, right, in these experiments, we have a pulsed OPO for the photothermal heating part, but the probe laser is just continuous. Okay, so we're integrating, we're not resolving this in time. And Ken will talk about later in this webinar about some experiments that his lab has done where you use you time the heating and the probe pulse together and what you can get out of that. I'll talk about one application of this that's a little bit different. So we use these experiments to look at the mid-infrared, basically Fabry-Perot modes of gold nanowires. On the left here is a SCM image of the wires. They look pretty crappy, right? But they were fabricated by electron beam lithography, so that's why they look a little bit chunky. The advantage of electron beam lithography is you have very precise control over the dimensions, so that's nice for the experiments. When we record spectra, we see some peaks, and we can assign them to what are called Fabry-Perot modes in these wires. They're basically standing waves of the electron density. The labels here, we work out both from the frequency of the peaks and also from looking at the images. So if you look at the label or the image of the modes that we've labeled m equals 3, you can sort of make out a 3-lobe structure, which corresponds to a, which is consistent with that order of the Fabry-Perot modes. In these images, because we're using a continuous probe, the structure of these plasma resonance is going to be very much washed out by thermal diffusion. So maybe it's even a little bit surprising that we saw them at all. We compared these to some COMSOL simulations that were actually done by David Masiello's group at the University of Washington. And you can match up the resonance, both actually the frequencies and also the line widths quite well. I think one thing to say about that, if you just thought about this a little bit, you would only expect to see odd order modes in these Fabry-Perot resonances. We see both the odd and the even order modes because the infrared light that's exciting the modes comes in at an angle, and that's the reason that excites the even order modes. And the thing that we can get out of this is that we can measure both the frequencies, of course, which you just saw, but you also get measurements of the line width, and that's shown on the right. And I think the thing that's interesting, why I sort of still talk about this a little bit, is that the line widths here turn out to be quite narrow, right? So when you look at gold nanorods, you expect that the minimum of the line width ought to be about 60, 70 millieV, determined by the Drude relaxation of gold. You can see that our line widths are narrower than what you would expect based on what's been measured about the dielectric constants of gold. And that's shown as that sort of orange shaded region. There's a bit of uncertainty in the literature about the best values. So that's a little bit surprising. You get such narrow line widths. And the reason is that the fields are basically mostly on the outside of the structure. Okay, so I want to talk about spatial resolution a little bit and how that's related to thermal diffusion. And so I think I had a very inaccurate way of thinking about this when we started these experiments. So these are some images of some gold, rather large gold nanoparticles taken at different image sizes. They're all done just exciting with a green laser and detecting with a 670 or 640 nanometer laser. I don't think it matters too much which it is. And these images were taken at different modulation frequencies for the pump laser. So if we just calculated the thermal diffusion, right, at a kilohertz, you'd expect a thermal diffusion length of about 6 microns. And at 100 kilohertz, which is the sort of range of the experiments here, it would only be about 0.6 microns. Now, when you look at the images, of course, you see nothing at all like that in these experiments. And these experiments were done in the regular way, in that we focused both the pump and the probe at the sample, and we scanned the sample through the pump. Okay, and so basically what's happening here is that, well, you only get a signal when your pump laser hits the particle, and so the spatial resolution is just basically controlled by the pump laser. So we thought that maybe that we could start to see these effects as if we did a wide field pump experiment, which is a little bit like what you do in the IR. Okay, and so this is what the images look like when we now blow the pump laser up so that we're always exciting the sample. And now we're scanning, again, the sample through the focus of the probe and doing this at different frequencies, okay? We can't go to very low frequencies here because of the signal noise, so we only went down to about 10 kilohertz. Okay, so now you start to see a little bit of an effect in the image. So at very high frequencies, the full width half maximum is about 1.15 microns, and it goes up to about 1.3 microns at lower frequencies, and you can kind of see that fairly clearly in the images. But of course, that is nothing like the thermal diffusion length that you would calculate, right? It's much, much, much smaller. Okay, so this was a bit of a surprise to us, but maybe because we hadn't thought about it very accurately. And so we did some simulations of thermal diffusion away from these small particles as a function of time. And so these are some simulations that are done in COMSOL for a 50 nanometer particle in glycerol. The different color lines are from the COMSOL simulations, and the dashed lines are from a formula taken from Castle and Jager's famous book. Okay, so what we're doing here is that we are starting with the sample at some temperature, 300 degrees Celsius. We're turning on the pump laser, and we're just looking at the temperature distribution in the sample as a function of time. Okay, so as you turn on the pump laser, the sample starts to heat up, and the temperature in the gold particle rises, and also the temperature starts to expand around the particle due to heat diffusion. So what you see here is that when you leave the laser on or you leave the heating source on for a long time, you eventually reach a steady state condition, right, where the heat going into the particle matches the heat diffusing out into the environment, right? And before that, you're sort of heating up, you're not reaching steady state. Now, the key sort of point about doing this is that when you reach steady state, the temperature distribution around the particle just simply goes as 1 over the radius of the particle, right? So what happens in these experiments is that for small particles, you kind of very, very quickly reach steady state. And once you're at steady state, it's all just 1 over R. And so there isn't really much of a reason to expect a difference in the way the images look when you do things at different modulation frequencies, because you'd rapidly reach steady state. Okay, and so it's basically for small particles, steady state comes very quickly, so you just don't see much effects in the photothermal images. These are some other simulations that sort of try to back that up. But the message I want to say is that when you 20, 50 nanometer particles, you've reached steady state so quickly that you don't see any changes in what the images would look like. And of course, the refractive index changes in the environment and in the gold compared to the environment are very much localized around the particle. So this is why you don't see much in we didn't see much in the images. Okay, so one way that we could possibly start looking at heat dissipation is to just slow that down, and you could slow that down by looking at much larger objects. So we started to do some experiments on micron-sized beads, and the ones I'll show are all on 6-micron beads. These are dye-doped beads, so we're actually doing this with a visible pump laser, but you could also easily do this with an infrared laser if you wanted to. And so there are 2 images here. One's a reflected light image, one's a photothermal image, and of course they're unfortunately not the same sample. So the most interesting thing you see here is that there's a ring pattern, right, in the beads. It's both in the reflected light and the photothermal image. And this comes about by a combination of diffraction and internal reflections in the bead that give rise to these rings. And so what I think is important to note here is that we actually kind of see these ring patterns whenever you look at visible light images of large beads, but that ring pattern survives in the photothermal image as well. So this is a bit more of a higher resolution image of the scattered light and photothermal images. On the top, we have reflected light images and PHI measurements done in reflected lights for these beads in air, so they're on a glass surface in air. And at the bottom, we have coated the beads with a organic medium, and now we're doing the experiments in transmission mode. So we see the ring patterns and these diffraction, internal reflection effects in both transmission, reflection. The images look a little bit different between the two. You can see two things when we're looking at the photothermal images. Firstly, the ring pattern survives. And secondly, when we do things in an organic medium, now we have see very clearly that in the photothermal image, the bead looks larger than its physical size, whereas you don't see this in the reflected light image. Okay, and I'll try to explain that again by using some simulations. And so that's the important point just noted there, right? The beads are larger than their physical size in the PHI images. So actually, if you're doing PHI images of large objects in a condensed phase medium, that's something that's a problem, right? You have to worry about. And this is our explanation. Okay, so it gets back to a little bit to those first cartoons of what we were showing when you heat a bead and you have it in air. So on the top, we have the temperature changes and the refractive index changes. Sorry, I should say on the left, we have temperature changes and refractive index changes for a bead in air on glass. And on the right, we have the same calculation for a bead in glycerol on the top of the glass. So if you look at the air, it's sort of what I tried to show before. There's a large increase in the temperature in the air from heat transfer from the heated bead into the air. The temperature at the interface between the bead and the glass is small because the heat is flowing very effectively into the glass. You don't see any temperature change in the glass on this scale because of the large heat capacity of glass. If you translate that into a refractive index change, in the air case, right, there are large changes in the refractive index of the bead, okay? And so that's what's giving rise to the photothermal signal. It's the difference, the photothermal signal is the sort of the difference between the heated and the unheated case, and so you're looking at the changes in the refractive index. So because the changes in refractive index are only localized in the bead, you know, the effects that are outside the bead basically cancel out. And so when you look at the photothermal measurement, you only see rings that are within the physical size of the bead. If we do things in an organic medium, now you have a temperature change in the glycerol from heat transfer from the beads to the glycerol. It's lower because of the thermal conductivity of glycerol. But of course, in glycerol, you get a significant change in the refractive index. Okay, so now there's a change in the refractive index outside the bead, and it's that change in the refractive index from heating outside the bead that's leading to this ring pattern external to the bead when you look at the photothermal image. And so if we go back here, right, when we have the beads in air, we just basically see, hopefully you can see my pointer, right, there's just ring patterns inside the bead because we're only changing the refractive index of the bead. Nothing's happening outside the bead. When we do things in an organic medium, we of course are changing the refractive index of the bead, and so we see a pattern changes in the ring pattern and the signal inside the bead, but we're also changing the environment, and so we're affecting the transmission, in this case of the probe, outside the bead, and so you pick up effects external to the bead, and the images start to now not actually accurately represent the size of the bead. Okay, and that comes about from the heat transfer of the glycerol, which changes the refractive index of the glycerol. If you were to want to do this to sort of quantitatively measure the size of the bead, well, firstly, it's a bit difficult if you have a condensed phase medium, right? Because you're going to have this effect where you're heating the environment around your object. However, the other thing that we would worry about is that, well, this ring effect is sort of going to hide any internal structure of the bead, right? And so you would need to get rid of that. So to do that, our approach was to destroy the spatial coherence of the light, and the way that, oops, actually, that's going to be the next slide. Okay, so the whole reason to get into this, right, was to look at how things might be changed if you change the repetition rate and you start to change the heat dissipation times. Actually, not much changes. You see, if you change the repetition rate of the laser source, you do see some changes in the internal structure, just basically because you're getting different magnitude of changes of the refractive index. So you can see for either the beads in the air, the internal ring patterns change much, but the physical size doesn't change too much in these images. But there's sort of clear differences in these different images. It's because the magnitude of the refractive index change is different when you do things at different repetition rates.
Excuse me, Greg, 5 minutes left until the end of the talk.
Okay, I'm going to be, I think, done well before then. Okay, so if you wanted to learn about the structure of this object, right, the ring pattern is a bit of a problem, so it'd be nice to get rid of that. So we think that this comes about both through a combination of diffraction effects and also internal reflections, which you might loosely call whispering gallery mode sort of things in the bead. And so those come about because you have a coherent light source when we're doing the imaging. So we tried to get rid of that by using an incoherent light source, just using a little laser LED. And of course, to get any reasonable resolution under the microscope, right, we wanted a collimated beam. So the way we did this is we took an LED, we focused it through a pinhole and recollimated to make a sort of, as close as we could, a collimated incoherent light source. And then we just did our reflected light and photothermal images with this light source. So if we look at the reflected light images right now, the spot size is basically the projection of the pinhole onto the field of view of the microscope. So the spatial resolution is terrible in the reflected light image. But when you look at the PHI image, it's pretty good. And now we've also got rid of the ring effects from doing this. The signal in photothermal signal, as you might imagine, is quite small. It's small for, I guess, well, a couple of reasons. One is that we don't have that many photons now hitting the detector when we use an LED that we're focused through a pinhole compared to a laser. And so now actually we start to see quite a bit of, if we turn off the probe laser, we start to see fluorescence from the beads, which we never saw before. At least in this experiment, though, that's still quite small in the photothermal signal. And of course, the other thing that we might worry about is that you're kind of detecting, you have a lot of light going through the sample that's not going anywhere near the bead in this experiment. And so that's not really contributing much to the photothermal signal. And so, maybe you could do better if you made the pinhole smaller, so you made a smaller spot size. And that leads to a rather nice set of images here, but it actually doesn't really help the photothermal signal much. So these are scattered light, photothermal, and also fluorescence experiments done by focusing our LED through a 200 micron, 100 micron, and a 20 micron pinhole. And so you can see as you start making the pinhole smaller, you do sharpen up the scattered light image as you would expect. You're just basically projecting the pinhole onto the sample. It becomes at 25 microns. It's not clear that we've done this focusing quite right because these scattered light images look a little odd now. This may be seeing some effects that are, maybe they're real, but the photothermal signal isn't really improved much. Right, we're in some sense helping the experiment because we're focusing to a smaller spot, so the photothermal effect is sort of you're affecting more photons out of the whole number of photons that are coming off the sample. But of course there are less photons, and so you're losing signal that way. So it would seem like 100 or 200 micron size pinhole is the best way for doing this measurement. And again, you can get rid of the ring effect, and maybe that's an advantage if you're trying to look at things that are internal to the bead. So these are our conclusions of this. So firstly, you look at spatial resolution. If you do these experiments in the normal way, that you focus your pump and probe through a very high NA objective, then your spatial resolution is just going to be determined by the pump beam. When you have a large pump beam, which you can do in a wide field measurement, or when you use an infrared pump laser, for example, then the spatial resolution is determined by the probe. So that's good for IR measurements, and but potentially has some problems when we're looking for heat diffusion. When we look at nanoparticles, we don't really see much effect from thermal diffusion, and we think that's just because the system reaches steady state so quickly that the temperature profiles are just 1/r around the particle, and so it doesn't really matter what modulation frequency or time scale you're looking at. It's just you have the same basically temperature distribution. And the last thing was these for micron-sized objects, you get these diffraction internal reflection effects. You can get rid of them by using an LED source, and for some applications that might be helpful. And I'll stop there. I wanted to say, Michelle mentioned that we have there's a connection to the Journal of Physical Chemistry, and the Journal of Physical Chemistry will be running a special issue dedicated to this set of webinars. So if you have a paper on photothermal or iSCAT or whatever sort of measurements you're interested in, we'd certainly like to have it for the special issue. I'll make sure that we have the email address for my editorial office on the website. So if you have questions about this process, please just let us know. But to some extent, it just amounts to writing a paper and submitting it and saying in the cover letter that you'd like to have the paper considered for the special issue on photothermal microscopy, or whatever the title is. And with that, I'll end there, and so be happy to take any questions. Thank you.
Thank you very much, Professor Hartland. Are there questions? Just speak up if you, or use the raise the hand sign. Maybe you can start with one. I was wondering, I know it's a difficult problem because we wanted to think about it. It's hard. What happens if you take now a plasmonic particle instead of dielectric bead, a plasmonic particle whose plasmon resonance depends not only on the index of refraction far away, but also on the refraction distribution, refractive index distribution close to the particle, a sort of skin effect, right? And now, depending on the time or depending on the modulation frequency, this plasmonic effect will somehow interfere with the scattering of the thermal lens that you create. So have you considered that in a simulation, that you might have specific effects of the particle scattering itself that may depend on the surrounding medium, and especially on the index and temperature gradients in this medium?
Yeah, so I'll answer. Well, I have two comments. I don't think I have an answer. I have two comments on your question. So the first one would be, maybe this is the most direct one, is to say, well, I think that Stefan Link and David Masiello have done more of these simulations that you're specifically talking about, because they have a paper out on how the photothermal signal depends on the size of particles.
It seems to me that in their theory, maybe I'm mistaken, but I read the paper, but it's a time ago, that they consider only steady state. So what what I'm driving at is that, in fact, by looking at different times, you are looking at the heat propagating in the surroundings, and of course the plasmonic response will or may differ depending on what is the refractive index, especially if you modulate. For example, you see that you can have a high index far away and lower index close by if you stopped heating, for example.
Yeah,
or vice versa, right?
So we did do some simulations on the change in refractive index of in the first part of the talk, we were looking at small particles, the gold particles. We did do some calculations of the change in the refractive index of the particle compared to the environment. So I can kind of remember this off the top of my head, or so I think basically there are effects. I haven't actually calculated I think what you want is a calculation of the scattering cross section, and it would be even better to do what Frank and also David Masiello have done, which is to then couple that into a transmission of the probe. Okay. So I think we could do that. We just simulated the refractive index changes. The refractive index changes in the particle are, of course, localized in the particle. And we did not calculate, I think what we have to do is calculate the actual scattering cross section and how that changes.
Yeah, correct. I mean, so maybe we better keep the subject for the general discussion, because maybe not everyone is interested in this very special case. Subhasis Adhikari has the question, so please go ahead.
Yeah, I think first I think nice to see this, how this micron size particle behaves differently than nano size particle in terms of spatial resolution. I had actually similar thing in mind to not only do the simulations but to do the experiment also. If you change different diffractive index in the medium, and how this even for this larger size particle, how this spatial resolutions is changing. In terms of that, I was thinking also that your images are amplitude image. So if you look at the phase image, and then probably it has a much more information in this ring patterns kind of objects.
Yeah, that's an interesting point about the phase image. So phase imaging in our hands is a little harder to do than when we just run it through a lock-in amplifier, and so we don't have very good phase images. It turns out, and for reasons that are not exactly clear to me, this was actually in our hands a rather hard experiment to do, and I think maybe because we did this with a visible laser, because that gave us better control over parameters such as being able to modulate it than with an infrared laser. So maybe we should be trying this with an infrared source. But we don't, the signal to noise in these images, even though the objects are large, is not all that great. And so the phase images were not very good. We also tried to do this in X and Y, which is maybe even better than the phase imaging. And that also was quite noisy and difficult to reproduce. The phase imaging would be interesting, and maybe we should try that again, because, in principle, that gives you information about time constants. That's been well established in photothermal microscopy. And so, but the images weren't all that great in that.
Thanks. Okay, can I have a last question, or keep it later?
There is another question by Cherung Xie.
Okay, thanks.
Well, thank you very much for the great talk. So I have the question about the coherence of the light source. So it seems to me that, I mean, photothermal detection is an interferometric detection of the thermal lens. So it seems that we need some sort of coherence to detect it. But you show the data that when we have too much coherence, then there's an additional effect that is difficult to model. So my question is it true, or can you comment on whether there is an optimal coherence for a given object of interest, and in terms of both spatial and temporal coherence? And I'm thinking about whether is there any ideal light source for these, a pulse laser, for example, that has you can tailor the temporal coherence, etc. Can you comment on that?
I can, like all of the answers to the questions, I don't think Ken Kuno is here, or Jixing Chen, but my understanding is that the way that they're using these lasers that they got from Thor Labs that are a little bit better than LED, but still not particularly coherent. So they have got a laser that they currently use lasers that do have rather poor coherence, that are somewhere in between, I guess, but they're somewhere in that region that you're talking about, right? That they're sort of you know, it's still a laser source, but it's or maybe it's not. I think it's still a laser source, but it's not a very good one, and so it's a little bit incoherent, and that helps wipe out some of these interference effects and diffraction effects that are basically not helping the measurement, but not so incoherent that you can't direct all the photons where you want them to go. So Ken is talking later in the webinar, and so I can go down the hall and send you an email about what that laser is, or look it up in Jiseng's paper. He'll talk a little bit about that too. So I think your feeling is kind of right. There is a sort of a sweet spot maybe where you sort of help. This is not really a problem for small objects, but for larger objects, you start to see these effects, and it becomes a little bit, it becomes more difficult to point those out. But I can send you a reference, I think, to
that. I appreciate that. Thank you very much.
All right, I think I see no more questions. So Subhasis, you can go back to your question now.
Yeah, I have this similar related to question. So if I see your images with the incoherent light, and it looks to me like the spatial resolution is smaller than the coherent light, which is in contrast to my intuition, because I will expect that if you have more coherence, so you will have a better spatial resolution. So is it true, or what is still here this spatial resolution for photothermal images? It's
okay. So we're talking about this image here.
yes, but with comparing with when you measure with the coherent light.
Okay, so so the spatial resolution here now, and maybe I should have mentioned it. So now it just becomes the pump again, right? So we're using a visible pump, right? So in the photothermal images, we're now just limited to the pump laser, and so I think is that what you're asking here, the spatial resolution in the photothermal?
But you are still using the, so here the photothermal image, the spatial resolution, is it similar to what you did with the coherent laser light, or because
Yes.
the image looks smaller, because I don't know the scale word, so that's why.
Okay. So I think the way to see that would be to look at this image here. So on panel D, that is a photothermal image of one of the beads, and the circle there is 6 microns, right? So
Okay.
So the spatial resolution now is just the bead in this measurement. For curiosity, right, we'd like to try to do this for nanoparticles, okay, but we haven't been able to get that to work, right? So maybe it's not a surprise that you can do this with 6 micron objects, but if we did this for a small nanoparticle, maybe that would be a bit more interesting, where you use an incoherent light source to as the probe in the experiment. But that hasn't worked yet in our hands. We couldn't get that to work with gold particles, but we're going to try some other nanosamples.
Yeah, thanks.